Any feedback from your end? Because then it's easy for me to move forward. Okay, if it is not the case, so I'll basically summarize few things. So during this first couple of sessions, we cover these two elements. One is the capacitors. So the other one is inductor. So we have capacitor and the other one is inductor. It's just a coil. So the value of the capacitance is basically in C. So this is the inductance. So this is in farad. This is in Henry. So if it is a capacitor, so we can obtain a kind of a relationship between the current and voltage. So this is the relationship. IT, the current flow through the capacitor is equals to the C times the derivative of the voltage apply across the capacitor. So this is the current flow through the capacitor. So this is the voltage applied across the capacitor. So keep in mind this VT basically gives the actual voltage appear across the capacitor, not the supply voltage. This is the applied voltage across the capacitor. So this is applied voltage across the capacitor. Across the capacitor. So this is the induced current, which is equals to C times the derivative of the voltage. So from this, you can basically extract expression for the voltage. Vt, the actual voltage appear across the capacity is 1 over C, 0 to T, I tau, d tau plus V0. So this is the initial condition of the capacitor. So initial condition of the capacitor. So this component basically covers the future values, because this integral goes up to t, which is a t is actually greater than or equals to 0. Main things. Okay, so so how do I accommodate that? So how many Tamil students in your batch?
As 20 students.
Sorry?
20 students. As
70?
20.
20. Because I can't talk in English, sorry, Tamil. So then it's not fair to use Sinhala. So that's the issue. Like if somebody wants to explain it in Sinhala, so we'll have separate chat. I mean, like it's unfair to utilize the same slot. So if you have anything, so I'll explain in Sinhala in different fora. For example, if you just drop an email to me, so I'll anyway catch you on Zoom and we can have a discussion, or through a phone I can explain. Doesn't matter, but so this discussion, I mean, it's not fair to do it in Sinhala because I can't speak Tamil. So then only I can summarize either both in Sinhala and Tamil. So extremely sorry. Anyway, so what I want to highlight here is, so you basically aware about these two equations. So this is the relationship between the current and voltage. So this is a kind of a fundamental mathematical model explaining the relationship between current and voltage of the capacitor. So either you have to keep in mind, if it is online exam, so you can get it from lecture note or somewhere, I don't mind. So then you can immediately get expression for the VT because this is a kind of a derivative. So you can remove the derivative by integrating both sides. So once you integrate it, so this is the constant appear in this integral, because so once you integrate it, it's a kind of an indefinite integral without this lower and upper limit. So that then you can introduce a kind of a constant. So that constant appear here as the initial condition of the capacitor. So this integral capture the status of the capacitor from 0 to t. So t is a kind of a value which is greater than or equal to 0. So this is a kind of a random variable which basically represent the value in between 0. It's basically in between 0 and t. So this integral capture the status of the future. So V0 is the initial condition of the capacitor. So if you want to find the voltage across the capacitor, you basically have kind of idea. So what's the current status, which means like the initial condition. Then based on the initial condition, you can basically capture the trends in future. So once you solve this integral, and if you just add the initial condition, you can get the values, voltage behavior t equals whatever the value. For example, if you want to evaluate the value at 1, so this would be like Vt 1 over c. So this integral goes from 0 to 1. So you just integrate the current, then add the voltage at t equals 0. So this is the voltage at t equals 0. So then you just add the integral part. So it gives the value at t equals 1. So this is t equals 1. Again, like, so you basically need these two equations when you are dealing with capacitors in a circuit. So this is a expression which directly express the current as a function of voltage. So this integral basically express the voltage across the capacitor as a function of current. So keep in mind, so this value should be there. Otherwise, you can assume it as a 0. So normally in questions, this basically gives, so it may be 0, it may be a non-zero value. So depending on the value, your whatever the voltage should be simply vary. So then, similarly for inductors, so we can find the induced voltage across the inductors like this. So it basically proportionate to the derivative of the current. So this is the current flow through the inductor. Current flow through the inductor. So IT is the current flow through the inductor. So the current flow through the inductor. So if you just apply a kind of a time varying current across the inductor, it basically induces a kind of a voltage EMF. So the value of this EMF for the voltage is simply equals to L, the inductance value times the derivative of the current. Similarly, so you can easily get a expression for the current across the inductor, which is equals to this. Let's see. So here, this is the initial condition of the inductor. So see, like if you refer the capacitor, so initial condition would be a kind of a voltage. So if it is an inductor, your initial condition would be a kind of a current. So these are the important equations. So this basically capture the past trends or the values up to t equals 0. So from zero onwards, this integral basically capture the trend. So these are the two expressions or equations which may use to model the inductor. So this is the very fundamental or preliminary equation or the mathematical model which explain the behavior of the capacitor. This is for the inductor. So again, we can again can come to a kind of a conclusion by looking at these expressions. For example, for capacitor, so this is the relationship, C times the derivative of the voltage. So what happens if this derivative is 0? So we know that derivative may be 0 for these two cases. One is the voltage would be 0. So the applied voltage across the capacitor would be 0. So then definitely the derivative would be 0. So other than that, if this time varying quantity become a kind of a constant, we note, so then again the derivative would be 0. So if this time varying voltage is a kind of a constant or 0, so then definitely the derivative would be 0. So what happens if this derivative goes to 0? The induced current is basically goes to 0 because this quantity is 0. So from this, we can argue that if you apply a DC voltage, so the DC voltage is a kind of this. So this is your time axis. So this is your DC voltage, like 5 volt. So this is your, so whatever the voltage appear across this terminal is fixed and constant throughout the time which we are interested. So for example, if it is like 10 seconds, so from 0 to 10 seconds, if this source is applied kind of a 5 volt constantly, so it would be treated as a DC voltage. So it can be treated as a DC voltage. So this is DC. If it is something like that, so this is not a DC quantity. So it's a kind of a AC, alternating type. So this is direct. So this is DC type, this is AC type. So if it is a DC quantity, DC means just keep in mind it's a kind of a constant and fixed throughout the certain time period. If it is fixed and constant, your derivative would be 0 and the induced current is 0. So then, what about if we apply a DC voltage to capacitor? If we apply a DC voltage, Vt is V0, it's a kind of a constant. What happens to the derivative? The derivative becomes 0 and there won't be any current flow through the capacitor. So then the induced current is 0. So then we can think of, rather having a capacitor, we can think of a kind of element like this, open circuit element, because once you apply kind of a fixed voltage to the capacitor, so there won't be any induced current. The current is zero. So then the capacitor acts as a kind of open circuit element. So we can basically conclude that this capacitor acts as a open circuit element. So then when we are modeling a circuit, or if we are simplifying a circuit in DC domain, DC domain means if we are dealing with DC voltages and current, we can basically treat this capacitor as an open circuit element. So it's the conclusion. Because once you apply a fixed voltage, the derivative would be zero and there won't be any current induced across the capacitor. So from that, we can basically argue so this is like so we basically get this conclusion by looking at this expression. So this is the fundamental equation which basically explains the capacitor. Current equals to C times the derivative of the voltage. Okay. So then what happens if this derivative goes to zero? So then you can see that you don't have any current here, because once this derivative goes to zero, C times zero gives zero. So then if the derivative is zero, you can't see any current. So the current would be definitely zero. So we can identify two scenarios where this derivative goes to zero. One is zero voltage. So if you don't apply any voltage across the capacitor, so then definitely derivative will be zero. So this is the first case. The applied voltage is zero. So the second scenario is if you apply constant voltage, like V0, like 5 volt, 10 volt, constant. So if you apply constant voltage across the capacitor, so from this mathematical equation, we can simply claim that derivative should be zero, because for the constant, derivative is zero. Okay. For the constant, derivative will be zero. So then we'll map this scenario into the physical scenario. So if Vt is a kind of a constant, means we are applying a kind of a DC voltage. DC voltage. So once you apply DC voltage, it means throughout the time which we are interested about, the applied voltage is fixed and constant. For example, if you take the DC power supply, set the voltage to 5 volt and apply to capacitor for 1 minute. So during that 1 minute, you are basically applying 5 volt to the capacitor. So it's a kind of a DC voltage appear across the capacitor terminal. So then for this scenario, if you apply a DC voltage source, we know that DC voltage, so the derivative becomes zero and induced current is zero. So then we can simply claim that if you apply constant voltage across the capacitor, so the induced current would be zero. So induced current would be zero means, so if we just think about this open circuit element and short circuit element, if it is a short circuit element, there's a current flow through the device. If it is open circuit, you don't see any current flow. So we can map that condition to open circuit element. So this capacitor acts as an open circuit element. Once this capacitor acts as open circuit element, you can't see a current. So that's the conclusion we can make it here. So if you apply a DC voltage, you can't see any current flow through the capacitor, then you can model it as an open circuit element. So this is very important once you simplify a circuit in a DC domain. A DC domain means if you are referring a DC voltages and current in a circuit, For example, if your circuit is simply powered by a kind of a fixed DC source, so then you can treat, if you want to analyze the circuit, you can basically treat this capacitor as an open circuit element. For example, we'll take a small example, a circuit here, capacitor here, and you have a 5-volt source. So for this capacitor scenario, you can basically think like this. So this is a fixed DC source. So once you apply a fixed DC source, this capacitor acts as an open circuit element. So then you can simplify to, if you are dealing with DC, and just replace the capacitor with open circuit element and solve the circuit. Now, for example, if you are asked to evaluate the current at t equals 1 second or like 10 seconds, so you can simply say that without any deeper knowledge about this transition. So you can simply say that this is a constant voltage. So after 10-second times, we can say that so this capacitor is facing to a DC voltage. So can be replaced with open circuit element. So you can't see any current flow through this one. This is zero. So kind of a conclusion can be made easily for capacitors if we are dealing with DC quantities. This is not valid for the AC. If it is a time varying constant, this is definitely a non-zero value. So you can simply define a derivative now. If the function voltage is something like that, this kind of time varying function, so you can basically define a derivative. If it is like this, so then we are in a trouble. If it is a constant, so derivative would be zero, and for such scenarios, capacitor can be replaced as open circuit element. Similarly, you can apply, so you can apply the same concept to the inductor as well. So for inductor, we know that the voltage across the inductor, so I'll put subscript L to derivative to, so this is the current flow through the inductor. So this is the induced voltage. So what happens if this current is a constant? So then the derivative would be zero if the current flow through the inductor is a kind of a constant, like capital I. This is a constant. So then if the current flow through the inductor, if the current flow through the inductor is a constant value, so then the derivative would be simply zero. So then similarly we can argue that, so then the induced voltage is basically zero. Induced voltage is basically zero because this derivative goes to zero. L times zero gives a zero value. So then what? So voltage zero means, so let's assume like there's a kind of an element here. Okay. So this is the VT and this is the IT. Let's assume you have kind of an unknown element and the voltage drop across this unknown element is VT and the current flow through the device is IT. What happens if you simply say that IT equals zero? So the current flow through the device or this unknown element is zero means, so this element acts as an open circuit element. So that's why you don't see any current flow. So then this element acts as a kind of open circuit element. So then only you can't see any current flow through the element. Similarly, you can argue that if the voltage is zero, so then the voltage across this, or the voltage drop across this element is zero. So then the potential drop here or the voltage at here and here are definitely equal. So this means VA, the voltage at point node A and voltage at node B are 0. So that's why the drop across this element is 0. So then if these two nodes having the same potential, you can simply treat it as a short circuit element. No? If this A and B have the same potential, you can just connect it through a kind of a short circuit, resistance 0 wire. So it's basically short circuiting. So then only the voltage drop across the voltage at A and voltage at B is exactly same. So if you introduce a drop across the device or the element, so then definitely VA and VB are two different values. So this if VA is not equals to VB, so then the voltage drop across the device is not equal to 0. If the current is 0 across any element, we can treat it as a kind of open circuit element. If the voltage drop across the element is 0, you can simply treat it as a short circuit element. So then you can treat this inductor in DC quantities as a short circuit element. Okay, so for the time being, just keep in mind, so in analog electronics, we basically use this concept. So when we are dealing with transistor biasing and so on. So for the time being, just try to understand. So I didn't do anything. I just take this fundamental equation and try to see what this equation behave in different scenarios. One is kind of a constant value. So for constant values, either capacitor or inductor, the derivative would be 0. Then the induced quantity is either a current for the capacitor or the voltage for the inductor is definitely 0. So then based on that, we conclude that capacitor act on DC quantities as an open circuit element and inductors act on DC quantities as a short circuit element. So this is the conclusion we made basically. Similarly, so we can argue this. So this is the voltage across the capacitor. C times the derivative of the, sorry, the other way. This is I. So this is the voltage applied across the capacitor. It's equals to the current is basically equals to C times the derivative of the voltage. What happens if this derivative goes to infinity? So the derivative means the gradient of the function. So if you say it in the practical sense, the derivative would be the gradient of the function. So if it is like this, so this is your function Vt. So this derivative is basically the gradient of this function. So this gradient would be definitely a kind of a time varying quantity depending on the point where you evaluate the gradient. For example, it's here. So your gradient is like this. It's here, your gradient is like this. So it's depend on the time you are focusing on. So this derivative again a kind of a time varying quantity for this scenario if it is a time varying function. So what happens if your voltage is something like that? So this is your VT. The voltage across the capacitor has this kind of a sharp rising or sharp falling edge. So this is a kind of a sharp rising edge. This is a kind of a sharp falling edge. So at this point, let's assume t equals t naught. So at t equals t naught, so the derivative is basically infinity. At this point, derivative would be, here it's minus infinity. For this case, it's plus infinity. If it is a rising edge, the derivative would be plus infinity. If it is a falling edge, derivative would be minus infinity. So you can think of like this kind of a slope. So then this is the gradient. So it's a kind of a negative value. So if you basically move it here, so it's converged to minus pi by 2. So that's why it's minus 9. So here it's minus infinity, here it's plus infinity. Anyway, it basically goes to either plus or minus infinity. So what happens if this derivative goes to infinity? So then for capacitor, this current also goes to infinity. So if this derivative goes to infinity, current also goes to infinity. So I'm not bringing any, alien type of concepts. I'm just referring the same equation and try to understand what happens mathematically. So if this derivative goes to infinity, then definitely current also goes to infinity because C is a constant. If you just multiply a infinite value with a constant, again the product is kind of infinite. So current goes to infinity. So then what happens? So we cannot gain any infinite current through a finite source. So mathematically, this is the scenario. Once your derivative goes to infinity, so definitely the current should be infinite. This is practically not possible. Because we are basically power this circuit through a finite DC source. So this finite DC source can have capacity of draining out a certain maximum current. If you use a 5-volt battery and power up the circuit, can this current goes to infinity? No, it's not. But this current can goes up to a kind of a maximum value. So in the practical sense, we can say that ICT goes to I max. So which is the maximum current which we can draw from the source. So this is the maximum current drawn from the circuit. So whether in the mathematical form, whether the current goes to infinity, in the practical sense, it means we can map it to this. So this current is simply jumps to its maximum. So if it jumps to maximum means, what happens to the rest of the circuit? Because we basically design a circuit for certain value of a current. Okay. Now it's visible, I guess. Yeah, sorry. So then we know that if the derivative goes to infinity, the current is basically jumps to its maximum. So then whatever the circuit is basically designed for a certain current rating. For example, you have a kind of a circuit. So this circuit is designed for current of 1 ampere. So source can deliver 5 ampere current. So this is the Imax which that particular source can deliver. So you have a circuit. So this circuit basically manage 1 ampere maximum current. So then you connect this circuit to a source. Source can drain out maximum of 5 amperes. If you basically make this derivative goes to infinite within this circuit, it means the source basically delivers 5 ampere current at that point. So if you maintain a kind of a sharp edge across this voltage capacitor, if you maintain this kind of a voltage across the capacitor, so then from this fundamental equation we know that the derivative goes to infinity and it basically absorbs heavy current from the source. So then the source deliver basically 5 ampere. The circuit which we are referring here is designed only for 1 ampere current. So then what happens if the source basically delivers 5 amperes, but this rest of the circuit is basically can manage up to 1 ampere means, so then this circuit is basically burned out. So based on this conclusion, we argue like, so capacitors cannot manage this kind of a voltage, sharp rising or sharp falling edges. So capacitors cannot manage this kind of abrupt changes, sudden ups and downs. It means the voltage across the capacitor should be very smooth. Smooth and continuous. So here you can maintain a kind of a discontinuity. No? So once you come from negative direction, it's converts to this value. If you come from positive infinity to here, it converts to this. So it's a kind of a discontinuous situation. So this capacitor cannot manage this kind of discontinuity. So based on that, we can say that the voltage across the capacitor should be smooth and continuous like this. So if it is like this, having sharp ups and downs, this capacitor cannot manage it, because from this mathematical model, we can say that current push it to infinity. So it's not possible in most of the scenarios. So we can claim that to avoid such scenarios, the voltage across the capacitor should definitely be a kind of a smooth and continuous function. So the VCT, the voltage across the capacitor, should be smooth and continuous function. If it is smooth and continuous, it means if we just pick a point t equals t naught. What about VCT naught minus VCT naught, VCT naught plus? So VCT naught minus means just before this point. This is T naught minus. So this is T naught plus. So if it is continuous and smooth, so we can claim that these three values are equal. T naught minus, T naught plus, and the value at t equals t naught. These three values are equal when this function is smooth and continuous. If it is like this, so if it is like this, So we know that T naught plus T naught minus are not same. So T naught plus is this, T naught minus is this. So these are not equals. So if it is smooth and continuous, we can claim that these values T naught minus, T naught plus, and T naught voltages at these points are equal. So this is the other conclusion we made out of the same circuit. So capacitors cannot manage this kind of a sharp ups and downs. Then the voltage across the capacitor should be smooth and continuous. So if it is smooth and continuous, we can basically argue that at any point the voltage is basically equals to the neighboring point. So this is the neighboring point. This is one. So these are neighboring points. At equals T naught, so the voltage value is basically equals to the T naught plus and T naught minus. Similarly, we can argue it. So this is for the capacitor. For the inductors, similarly. So the induced voltage, I hope this screen is shared. If not, just drop and text. So this is the induced voltage across the inductor. This is the current flow through the inductor. So if this derivative goes to infinity, it means you basically induce an infinite voltage across the inductor. This is also not possible. Mathematically, this is possible. Yeah, a capacitor not work means capacitor whatever the yeah, for this 5 volt source. So after a certain time, so this capacitor basically, so I'll explain this. So what happens to the capacitor when we apply DC? So I'll explain it in the next couple of slides. So just wait for a while. Function of the capacitor, the voltage. Yeah, so we can simply say that the function of one of the function of the capacity is the smoothing of the voltage, because it basically can buffer the voltage, or it basically act as a kind of a sink for this kind of a variation. So that's why we use these capacitors to as a smoothers for this rectifier circuit. So if you I'm pretty sure like you basically study this half wave and full wave rectifiers. For those cases, we use capacitors to smooth the waveform. So that's basically happen that this capacitor can absorb these sudden changes. Okay. So for the time being, we'll assume that it can manage the smoothing process. Yeah. So then this yeah, mathematically speaking, once this derivative goes to infinity, the induced voltage is basically jump into infinity. So this is not practical. So then we can claim similar argument. If the current flow through the inductor is smooth and continuous, so you can't get this kind of a scenarios. You can't get this kind of a scenarios. So then basically we can argue like in the previous T equals T naught scenario, the current through the inductor T naught minus equals to current T naught equals to current at T naught plus. So then capacitors cannot manage this, inductors cannot manage this kind of a sudden falls or rises in current. So these inductors cannot manage such abrupt changes in current. So it basically smoothen the current waveform as well. So if this is the current flow through the inductor, then we basically claim that this condition is true and satisfied. This is valid only for smooth and continuous scenarios. If it is a kind of a discontinuous model, if this current basically shows this kind of a discontinuity, you cannot assume this. So this is only valid for this situation, smooth and continuous situation. So this is the summary of this capacitors and inductor. We didn't do anything, so we just explain the circuit or explain the very fundamental equation mathematically in different domain. What happens to the circuit when this derivative goes to zero? What happens to the circuit when the derivative goes to infinity? So we basically explain or try to understand what happens to the circuit in these two domains. Derivative is zero and derivative is infinity. So once it goes to zero, we found that the induced voltage or current becomes zero. Based on that, we replace the capacitor and inductor using open circuit and short circuit element when the capacitor and inductor is in DC circuit, in DC domain. So then we found that once this derivative goes to infinity, the induced voltage or current would be simply jumps to infinity. So this is not practical in the normal scenario because it cannot drain out infinite voltage or current from a fixed finite source. So then we argue that capacitor cannot manage the sudden changes in their voltage. Inductors cannot manage sudden changes in the current. So this is the very simple summary of this capacitor and inductors. So based on this mathematical models, we'll move to the next block, next session. So the next session basically covers the first order circuit. So this is first order circuit. So up to now, we consider circuits containing sources. Either it may be a voltage source or it may be a current source. It may be dependent, independent, whatever the sources in the circuit, and as well as we have resistors in the circuit. So we basically consider resistor loads during circuit analysis. One, I'm not sure, sometimes you may deal with these inductors and capacitors. But in circuit analysis too, we basically deal with circuit containing capacitors, inductors, and both in addition to the sources and resistors. So whatever the circuits we discuss and try explain or analyze here contain capacitors, inductors in addition to these sources and resistors. So if you have circuits containing resistors and capacitors, we basically identify those circuits as RC circuit. So if you have resistors and capacitors in a circuit, so we basically identify it as a RC circuit. So if you have resistors and inductors, LR or RL, whatever LR circuits. So it basically contains resistors and inductors. So if you have all three, resistors, capacitors, and inductors, so they become RLC circuit. So then we can basically identify three type of circuit when we are dealing with capacitors and inductors. One is RC circuit, where you have resistors and capacitors in the circuit. LR or RL circuit, where you have resistors and inductors in the circuit. So if you have all these component resistors, capacitors and inductors in the circuit, it becomes a RLC circuit. Okay, so this entire study basically would be, in general, RLC circuits. In general, it would be like RLC circuits. So in circuit analysis 2, we basically study RLC circuits.
Tube light circuit.
Sorry?
Tube light circuit. I think.
Yeah. Sorry, I couldn't hear you.
No, sir. RLC circuit, just like tube light circuits.
Yes. So it's a one example. So there we have this inductors, capacitor, and a resistive load. Okay. So we have a starter there, choke there, and the resistive loads also. So it's a one example for RLC circuit. So you can find a lot of RLC circuit when you are dealing with this radio transmitters and receivers. So they have coils, capacitors, resistors, yeah, filter circuits. So we basically come across these inductors, capacitors, and resistors. So filters, then these transmitters basically. And a very simple example is a kind of a tube light, which basically this scenario is basically managed with this R and RLCN component. So the concept here is we can basically explain using this previous example. For example, in this previous couple of points we discussed, we found that once you change your current or voltage, so if you just drop your current or voltage suddenly, so what happens to the induced value? It becomes infinite, isn't it? If you change your voltage across these two terminals suddenly, so the induced current would be infinite. So in the other way, if your current is simply drops to zero from certain value to immediately drop to zero, if it is dropped to zero from some value a to zero, so then the induced voltage is infinite. So it means if you have these two terminals and we basically manage a kind of an infinite voltage across these two terminals. So then what happens due to this heavy potential? So whatever the free electron is, just push it, so the other way, push from this negative terminal to positive terminal. So whether it's a kind of open circuit due to this heavy potential managed across these two terminals, so the electrons are just released from this negative terminal and absorbed to positive. So it means like whether it's open, it simply there is a current. Appear a spark again. So so we induce a kind of a sparking scenario inside the tube light by managing this kind of a situation. So you can basically explain. So you just refer Google. So you can find the operation of fluorescent light. So you can mathematically explain it. So this is the scenario. We basically manage a kind of a sudden drop. So due to the sudden drop, whatever the tube light terminal across these two terminals of the tube, fluorescent light create a kind of an infinite voltage. So once it becomes infinite voltage drop, so whether it's open circuit, there may be a spark happens, like in the lightning. So you don't see any conductive space now. once you maintain a kind of a huge potential, so then there may be a kind of a current flow to the ground. So it's the lightning. So we can explain those scenarios using this very fundamental mathematical equations. So anyway, just forget it. There are a lot of applications, specifically filters, which you have this R, L, and C component. Okay. Yeah. So then, so we'll. So during this discussion, we basically considered two categories. One is with sources. So the other one is without sources. So it means we have a circuit. If the circuit is basically powered from an external source, so we can identify it under this category with sources. So if you have a source, so if you have a circuit and the circuit is basically powered from an external source, so like whatever the circuits now we are doing, so we build a circuit and use a 5-volt or 9-volt battery to power it. So it's a kind of a circuit which basically powered through a external source. External source means yeah. So what is external source? So if you go through this without sources scenario, you found that. So during this last discussions, we found that capacitors and inductors can store energy. Capacitors and inductors can basically store energy. So that's why once we discuss these capacitors, we discuss about the initial voltage of the capacitor. So once we discuss the inductors, we basically explain about the initial current of the inductor. So then it means these capacitors and inductors can act as a kind of a source. So capacitors basically act as a kind of a voltage source once it's charged to a certain level. Sorry, I guess my internet connection is not stable. Anyway, so what we discuss here is, so this capacitor, once you apply a voltage, so this capacitor can absorb certain amount of energy. So then capacitor basically act as a kind of a voltage source once it's charged. Similarly, inductor also same. So once you charge the inductor act as a kind of a current source. Okay. So then, so there may be a situation where you don't have any sources in the circuit, but the circuit is basically powered from the stored energy of the capacitor or stored energy of the inductor. So in this scenario, without sources mean the circuit is basically powered by the charged capacitor or inductor. So without source scenario, so the circuit which we are referring is basically powered by the capacitor Yeah. So what I want to explain here is, so just start with the without sources. So without sources mean, let's have, so you have a circuit, but you don't connect any DC source or DC supply to the circuit. So then ideally speaking, if you don't have any energy source you connected to the circuit, you can't see any current or voltage. It's very simple, no? So you have a kind of electronic circuit. So if you connect a battery to the circuit, it's not working. So, but there may be scenarios where if you charge the capacitors in the circuit, if you charge the inductors in the circuit, so without these sources, without the external battery, so this whatever the capacitors and inductors can power the circuit with the stored energy. So you may heard about this the charging of the capacitor. So you can charge a capacitor and a stored energy. Once you connect a charged capacitors to a circuit, so we had that once you connect a circuit, so there may be a kind of a discharging process. So it means this capacitor acts as a source at that particular moment, and whatever the stored energy simply released through the resistive load. Similarly, inductors can act as a kind of a current source. So once you charge your inductors, so then this inductor acts as a kind of a virtual source for this circuit. So then you don't need external power to power up the circuit. So whatever the stored energy of the capacitor and stored energy of the inductor can basically power up the circuit. So this without source category, we basically discuss those scenarios where you have a capacitors and inductors in the circuit. Those capacitors and inductors are charged to a certain level. So then these charged capacitors and inductors act as a virtual sources for this circuit, and these virtual sources deliver power to the circuit. So then this circuit is basically managed through the stored energy of the capacitors and inductors. So this scenario, we don't have any external sources. External sources mean so whatever the circuit is basically managed through the internal energy. Internal energy means the stored energy of the capacitor or stored energy of the inductor. So without sources, we basically discuss circuit where this circuit is basically powered or managed by the internal energies. Internal energies mean the energy stored in the capacitor or energy stored in the inductors. With sources means, so we have capacitors and inductors in the circuit, but they don't have any initial energy. So then to make them charge, we have to plug an external source, battery or a power bank or a kind of a DC voltage source. So in that case, so we are discussing the impact of sources. So those scenarios, so those categories, we have external sources, and through these external sources, we power up the circuits. We power up means we basically use this external circuit to charge the capacitors and inductors in the circuit. Then we remove this external source and utilize the stored energy in the capacitor and inductors to power the circuit. Okay, so I'll explain with a small example. So let's assume a circuit like this. So we have a circuit contains a two-way switch. So this is a two-way switch. So either this switch can position to 1 or position to 2 depending on our requirement. So this is a source. So once we position the switch to node 1, at 1. So what happens? So the source can basically power the circuit. So once you place this the two-way switch to position 1, so we have a source. It's something like that. So we have a RC circuit, and this capacitor is initially at 0 voltage, just assume it. So then this source basically charge this capacitor. So due to this circuit arrangement, so this capacitor is basically charged to a certain voltage due to this external source. So this is your external source. This is your external source. So once you position your two-way switch to node A, so then you can have a circuit where you have a resistor R1 and C capacitor, which is directly connected to an external source. So then this capacitor is basically charging. So this is the scenario which we identify as a with source condition, with source. Because this, for this case, this capacitor doesn't have energy to drive the circuit, and this external source is the one who charge or drive the circuit. So this is the category which we identify as with source. With source means the circuit is basically powered by an external source. So once you position into node 2, if you change your switch to node 2 after 10 seconds, what happens is actually, so we have this load resistor and this capacitor. So this is RLC, and this is already charged up to like Px. So this capacity is basically charged to Vx during this 10 seconds, which we connect this external source to the capacitor. So then now this capacity is already charged to a certain voltage. So once you move your switch from position 1 to position 2, so then capacity is already charged, and there isn't any requirement to have this external source in the circuit. So this capacitor, which is charged up to a certain voltage, can drive the circuit. So then you can see again a RC circuit, which is basically without any external source. This capacitor acts as a kind of a virtual source, but no any external sources to power the circuit. So this is basically identified as without source scenario. Okay, so in this case, so the capacitor acts as a source. So this capacitor act as a source means once it acts as a source, so there should be a stored energy. So that stored energy basically delivers power to the circuit. If you don't have a stored energy inside this capacitor or inductor, so you have to use external source to power those. So this is with source, which means like the circuit is basically drive through an external power supply, external current or voltage source. Without source scenario means you don't have any external voltage or current source like a battery or power bank or DC supply. So whatever the circuit is basically drive through the stored energy of the capacitor or inductor. So hope it's clear without source and with circuit scenarios. So with sources means we are dealing with external current or voltage sources. Without source means, so we are dealing with the internal energies of the capacitors and inductors. Okay. Hope it's clear. If you have any questions. So do you have any questions? Did you manage to identify the or recognize these two categories? What is with source and without source? Virtual source means, so there won't be any physical source there. So for example, if it is a battery, we know that it's a kind of a physical entity. So it's a physical source. But this capacitor is not a physical source. Once we charge the capacitor, it acts as a source for a particular period. It becomes a temporary source for the circuit. So that's why I use this virtual source. So it's not a physical source. Capacitor power is limited drive. Yeah. So it once you purchase a capacitor based on these capacitance of this capacitor, so it basically indicates the how much energy you can store inside the capacitor. So there's a limit definitely. So then what we can do is we can maintain this charge inside the capacitor. So the easiest way is like once this capacitor get discharged, so once this get discharged, you can again you can charge it. So how do you charge the capacitor? So you can move this two-way switch back to position 1. Then once it's charged, you can release the source and connect it to the position 2. Likewise, if you can move this two-way switch from position 1 to 2 and 2 to 1 so on. So you can charge the capacitor and use that power to deliver the power to the load. Then once this stored energy of the capacitor is releasing beyond a certain threshold, you can just connect it again to the source and charge the capacitor. Then switch it to position 2, deliver the energy to the load. Likewise, you can do it. Okay, so you can have a kind of automatic switch. You can do it. Once it discharges, you basically connect it to the source and charge the capacitor. Once it's charged to a certain level, you can simply connect it to a load and deliver the power through the capacitor. So this scenario is basically happening in this smoothing process in the capacitor once you are working with this full wave and half wave rectifier. So we'll discuss it in this analog electronics, but keep in mind, so this is the scenario where we are using for most of the circuit. If it is discharged, connect the source, charge it. Once it's charged, we'll basically disengage or isolate it from the external sources and connect it to the load, and then the power is basically delivered through the capacitor. Is it now clear? Any doubt? I hope it's clear up to a certain level. So if you refer the content, you can brush up your knowledge. Okay. Okay. So we'll now try to analyze one simple circuit. Okay. So this is a very simple circuit. So we have a resistor here. So we have a in charged capacitor. Keep in mind this is R. So this is already charged. Already charged means Vt equals V naught at t equals 0. So t equals 0 means the point where we start monitoring the process. For example, if we just draw the timeline, so this is the timeline. So this is t equals 0. Okay. So let's assume like we have a circuit. Now we try to understand the behavior of the circuit now. So once we start plug it to a kind of a monitoring mechanism. So then we are basically monitor the circuit. So the position or the point where we start monitoring is t equals 0. So then we can basically monitor the circuit, what happens to the circuit in future. So for values which is greater than 0, we basically capture the future. So but we don't know what happens to the circuit during this t less than 0. What happens to the circuit during this past. But we know the initial condition. Initial condition basically capture whatever the situations happen during past. So then we don't need to worry about what happens to the circuit during past, but with this initial condition, so we can manage the rest. If you know the initial condition or the voltage at t or whatever the conditions at t equals 0, if you know those values, you can predict or forecast the future. Okay. So now we don't know from which source this capacitor charge up to V naught and how it will take these circuit to capacitor to charge up to V naught. We don't know anything. But the only information we know at t equals 0, at the point where we start to analyze the circuit, the capacity is charged up to V naught. So this is the initial condition. So at t equals 0, the point where we start monitoring, we start analyzing, we start to forecast, we know that capacitor is at voltage of V naught. But we don't know from which source, at what time, how long it will take. We don't know anything. But we know only this capacitor is charged up to V naught. So from this point of, so using this, whatever the data we have, we try to analyze the circuit for the future. So this capacity is already charged to V naught, and we then connect it to a kind of a resistor. So by looking at this, we can identify that this is a scenario where we can categorize into without source. Without source means, so we don't have any external source to power the circuit. So we basically power the circuit using the stored voltage across the capacitor. So then this capacitor, for this particular scenario, this capacitor acts as a kind of a voltage source. So this is a kind of a temporary arrangement. So this voltage is basically act as a kind of a virtual or temporary source to the circuit. Okay, with the initial stored energy. Okay, so then we'll try to apply Kirchhoff laws and try to get a kind of a equation to explain the circuit, because the entire module is basically based on mathematics. So we try to explain the behaviors, explain the situations based on the mathematics. So that's why it's called circuit analysis. So the analysis is basically the ground form is mathematics. So we basically model capacitors and inductors in a mathematical way. So that's why we came with like couple of equations to explain the voltage and current across the capacitors and inductors. So we use those models to analyze a circuit. So then using those mathematical equation, we can give a kind of a hint about the behavior of the circuit. So then we don't need to implement it first and see. So we can analyze the circuit and we can give a kind of a hint or a clue about the operation of the circuit. Otherwise, we have to purchase the component. So we have to lay the circuit in a breadboard or somewhere. So then power it up and see. So in this case, we don't need anything. So if you have a kind of a mathematical knowledge, or if you can use a kind of a simulation tool, using that you can basically simulate the circuit without implementing it. So without any hardware, you can do it in the mathematical form or simulation platform and give a kind of a hint or clue about the circuit, how it's operate, what happens to the circuit at this condition. Like, so this is circuit analysis. So then, so we'll try to apply whatever the known circuit theories and formulas. So we'll apply, let's assume. So this is the current flow through the resistor. So this is the current flow through the capacitor. This is the node A. So I'll apply Kirchhoff current law for node A. Okay. So once we apply Kirchhoff current law, so we can simply say that whatever the current flow into the node equals to the current flow out from the node. So based on that, we can simply say that current flow out from the node is this, the sum of IRT and ICT. Flow out from the node equals to flow into the node. Nothing flow into the node, this is 0. Okay. So these currents are basically marked based on the passive sign convention. So we know that passive sign convention means, so the if you mark the current, then we can basically mark the or define the induced voltage across the element. So then the current is basically flowing into the positive terminal of the element or node. So this is then positive, this is positive, this is negative, this is positive, this is negative. Current flow into the node marked as a positive terminal, into the node positive. Okay. So based on the passive sign convention, we basically mark the induced voltages and currents. So then apply Kirchhoff current law for the node A. Then we found that the current flow out from the node equals to 0 because there won't be any currents flow into the node. So then we try to replace the current flow into the nodes in different way. Let's assume the voltage across the capacitor is VCT. So what about the voltage across the resistor? It's same. So the voltage across the resistor also VCT. So there won't be any other element to drop the voltage. No? So whatever the voltage appear across the capacitor is directly appear across the resistor. So then the voltage across the resistor also VCT. So if we apply Kirchhoff voltage law, we can easily identify VCT should be equals to the voltage across the resistor. Okay, VR. So from that, we can simply say that we can convert this. So we can convert the current flow through the resistor like this. VCT divided by R. So just apply the Ohm's law. I equals R, V equals I times R. So from that we can simply say that I current flow through the resistor is equals to the drop divided by the resistance. So the drop is actually VCT, same drop across the capacitor, and divide by the resistance. So you can replace the current flow through the capacitor from the fundamental equation or the model we derived just before. Here you can simply say that this is equals to this. C times the derivative of the voltage. This is equals to 0. Okay. So hope it's clear. So nothing different. So you just apply the Kirchhoff current law for the node A and replace this current with voltage. Nothing else. So then we can simplify or rearrange the terms and we can get this kind of equation. Okay. So we can get this kind of equation. So it means we can explain the voltage across the capacitor, voltage across the resistor, voltages in the circuit using first order differential equation. First order differential equation. Okay. So this is the first order differential equation. I believe like you basically cover this stuff in differential equation module in maths. So this is the first order differential equation because order of this derivative is 1. So you have a first order here, so it becomes a general first order differential equation. So then it means like the behavior of the voltage can be mathematically modeled using a first order differential equation. So such circuits can be identified as first order circuits. So first order circuits means if you can parameterize the voltage and current using first order differential equation, you can basically identify those circuits as first order circuits. So from this we can conclude like we may have this type of circuits as well, dnvt or dtn plus 0, dn minus 1, dtn minus 1, like that. So it means like we may have nth order circuits which basically explain the behavior using nth order differential equation. So there may be scenarios where you can explain the parameters of the circuits using nth order differential equation. So then this particular circuit become an nth order circuit. If it is basically explained through a kind of a first order differential equation, so then we can basically argue that it's a kind of a first order circuit. Okay. So from here, you can basically obtain, so once you solve this differential equation, you can simply get expression for the voltage. So did you cover this in differential equation module? So did you cover this? How to solve this first order differential equation? So I believe it's basically yes. So then I don't need to worry about that. So you know how to solve this one. So I'll just write the answer. VCT equals V naught e to the power minus t over RC. So you can basically refer that to the differential equation module. And then the solution for this first order differential equation which we obtain here is this. VCT, the voltage across the capacitor equals V naught. V naught is actually the initial condition of the capacitor at t equals 0 into e to the power minus t over RC. Okay, so this is the solution. So if you draw it, so it's something like this. So this is T, this is VCT, the voltage across the capacitor. So what about at t equals 0? So we know that at t equals 0, the voltage across the capacity is V naught. So then what happens that t goes to infinity? So this negative exponential function converges to 0. So then this is something like that. So this is V naught e to the power minus t over RC. This is the voltage across the capacitor. So if you plot it, this is the it's a kind of exponential decaying function, and the initial voltage is V0, and after certain time it basically decays to 0. So we'll discuss the time constant also here. So what happens when t equals RC? So there's a kind of a value. You can simply brought it by just multiplying the R value with the C value. So the R is the equivalent resistance of the circuit and C is the equivalent capacitance of the circuit. If you have multiple capacitors and resistors, so you can simplify it to a single resistor, single capacitor. So the product of this R and C gives the time constant. So this is basically indicated by tau. This is time constant. So time constant is a kind of a parameter which gives a kind of an indication about the rate of charge or discharge. If this time constant is very small, it means we can basically argue that capacitor can charge immediately and discharge immediately. If this time constant is relatively large and large, so we can claim that capacitor needs more time to charge and more time to discharge. So when this T equals tau, which is equals to the product of R and C, once you plug this T value here, we can simply identify there as a value for V naught divided by E. So this is the place where we define as the time constant of the circuit. If it is a RC circuit, so the product of this R and C gives the time constant of the circuit. If it is a R and C circuit, so the product of R and C gives the time constant of the circuit. So if you know the time constant, for example, if this time constant is very small, it means, so the behavior of the capacitor is something like that. So this time constant is somewhere around here. So it means like it can immediately discharge. If this time constant goes to 0, converts to 0, so you can see this kind of a discharge process, immediately discharge. Okay, so then it's like this, immediately discharge. So if the time constant is reasonably high, so it takes long time to discharge. So it takes long time to discharge. So this is the, by looking at the time constant, we can simply argue like whether this capacitor can charge or discharge immediately or it takes a certain amount of time. Okay, and again like, so we can put another information. So during 5 times tau, this capacitor can charge it to max or discharge it to minimum. So for example, if it is a capacitive circuit or RC circuit, so we know that once you plug an external source, this capacitor gets charged up to a certain value. If you release the external sources and you utilize the stored energy of the capacitor, it basically discharges the resistive loads and converts to 0 like in the figure explained here. So to convert it to 0 or converge it to maximum voltage, it takes basically 5 times tau times. So this is a kind of practical information we capture from practical circuits. So basically it needs 5 times the time constant time to either converge to 0 or converge it to maximum voltage. So this is the information we basically can capture from practical circuit. So keep in mind, so any RC circuit or LR circuit needs 5 times the time constant duration to convert it to 0 or converge it to maximum. So then during this charging, it takes 5 times tau times to charge it to maximum. Then remains as it is. So if it is a discharging process, whatever the voltage appears across the capacitor can discharge to zero completely within 5 times tau time. Okay, so this is a small facts you need to keep in mind, nothing else. So now at the end of this discussion, we found that there's a circuit. The capacitor has an initial charge. We don't have any external sources. Then the circuit is basically powered from the stored energy of the capacitor. So we consider a very simple circuit having a resistor and a stored the capacitor with the non-zero initial voltage. So then we apply the circuit theories and came across with a kind of a first order differential equation. So then we found that if these parameters, circuit parameters, can be explained through a first order differential circuit, this circuit can be recognized as a kind of a first order circuit. So first order circuits, the voltage would be like this. Normally it follows a kind of an exponential trend. It may be to the converge into a constant, or it may be converge into a zero. Anyway, the pattern aligns with the exponential function. Patterns basically aligns with the exponential function. So the initial value may be completely depend on the initial stored energy of the capacitor or inductor. So we found that. So we'll ended up with a kind of a differential equation. So previously we ended up with a kind of a linear equation with currents and voltages if it is a resistive circuit. So in circuit analysis 1, we basically deal with circuits with resistors. So then we found that we'll ended up with linear equations. So I1 plus 3, I2 plus something equals to a kind of a constant likewise. So those are like linear equations. So these are not linear equations. So for this scenario, if you introduce a capacitor to the circuit, or if you introduce an inductor to the circuit, we will definitely ended up with a kind of a differential equation. So the number of capacitors and inductors may give a kind of a hint about the order of the circuit, but it not always true. But certain very special cases, if you have multiple, for example, if you have n number of capacitors, there may be a chance to reduce this n number to a single capacitor. So then whether we have n number of capacitors, it won't be a nth order differential equation or nth order circuit. So there may be special cases you can reduce the order by reducing the capacitive effects by considering the series parallel combination. So by looking at the circuit, sometimes we cannot exactly say whether the circuit is an nth order one or a first order one or a second order one. But once you write these expressions or equations, you can easily find the order of the circuit. Okay. Second, now we anyhow managed to get a differential equation which basically describe the behavior of the voltage. Okay. So again we find that there is a kind of a quantity called time constant which explain the behavior of or the rate of charging or discharging process. So once we map this time constant to here, see this. So this RC product is appearing the zeroth order term. This is the zeroth order term. So this is the first order term. This is first order term. And the coefficient or the prefactor of the first order term is basically 1. And the coefficient of the zeroth order term is basically 1 over tau. time constant. Okay, 1 over tau. So keep in mind 1 over tau. So then if it is a first order circuit, by looking at the prefactor or the coefficient of the zeroth order term, you can immediately find the time constant. So let's take a small example. So you have a differential equation like this. So what about the time constant? This time constant is 1 over 5. So by looking at the coefficient of the second or zeroth order term, you can easily recognize the time constant. So then we can have a conclusion like, so in this previous circuit we can easily identify the values of the resistor and the values of the capacitor, because we have one capacitor and one resistor there. So then without going into this differential equation, we can immediately evaluate the time constant, because we know the value of the resistor and capacitor exactly. So by looking at the circuit, we can easily evaluate the time constant. But there may be certain circuits you cannot simplify it to a first order circuit. Whether they are first order circuits, there may be multiple capacitors. We can sometimes simplify it to a single equivalent capacitor, but it's hard to find the way of reducing the number of capacitors. Depending on the configuration of the circuit, sometimes it's hard to simplify the circuit to a single resistor or a single capacitor. So for that case, so we don't need to worry about that. So we'll take the differential equation and pick the coefficient of the zeroth order term and take the inverse of that. It gives the time constant of the circuit. So there are two ways. One, I mean, like if you ask to find the time constant of the circuit, one way is actually just get the product of R and C. So it gives the time constant. So if you have multiple capacitors and multiple resistors, and if you know that it's a kind of a first order circuit, so you don't, I mean, it's hard to find the effective or equivalent capacitance and equivalent resistance. So then you get the differential equation, and pick the zeroth order coefficient. So then tau would be 1 over that term. So if we just put like this is A naught, so this becomes 1 over A naught. So this is the time constant. So then you don't need to worry about the simplification of the circuit. Just if you feel like you can't easily simplify to a single capacitor and single resistor, just apply Kirchhoff voltage or current laws and try to obtain a differential equation. So if it is a first order differential equation, definitely the coefficient of the zeroth order term gives the time constant of the circuit. So then without just multiplying this R and C, by looking at the differential equation itself, we can get the value of the time constant as well. Okay. So hope it's clear. Any questions so far? Any questions so far? No. Seems you understood. Or No means like nothing. Anyway, so if you have any questions, just let me know. So we'll do like this. So I actually during this previous weeks also I just had a Zoom link to this Sims, but later on I found that it's not that visible to you. Anyway, so I'll use the similar way like today. So there's a you have a kind of a batch representative. I'll share the Zoom links with him. So I heard that you have a WhatsApp group. So then he'll drop it to the WhatsApp. But basically for analog electronics, so we as a norm, so we have this discussion class on Monday from 1 to 3. So it's the normal schedule slot. And for the circuit analysis, we'll keep this 9 to 11 slot to discuss the issues in circuit analysis. Friday 9 to 11. So then it's easy. So you can just log into the Sims, then you can find the link. Otherwise, you can basically find the link through your WhatsApp group. So analog electronics, we have a discussion class on Monday 1 to 3. Second, see directly. Yeah, so if you can, so there may be certain circuit you can easily find the R value and C value. So then for that those stuff, if you ask to evaluate the time constant, no need to get the differential equation, just take it, the product of R and C. Sometimes if you have multiple resistors and capacitors, and if you don't find a way to reduce it to a single capacitor and resistor, so you cannot find the equivalent resistance and capacitance. So then for those cases, there's a kind of approach. You just write equations and simplify to a kind of a first order differential equation. So then the coefficient of the zeroth order terms give a kind of a hint about the time constant. Yes, we have analog today from 11:15. So if somebody needs to clarify something, so you can come to the discussion. So from next week onwards, I don't know whether we have midterms. Otherwise, midterm schedule I have to check with. So otherwise, the norm is like Monday 1 to 3 we have analog one, and we'll continue this slot until the end of the semester. Friday 9 to 11 circuit analysis 2. Okay, so if you have questions, drop an email or drop a message to the discussion forum, or else we can discuss it here. So we'll meet on 11:15. Okay, thank you.